Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 5th, 2026, just about 5 days ago. It introduces a framework called Agentic Memory that allows agents to manage their own memory operations as tool-based actions, boosting success rates on complex tasks by nearly 9% compared to strong baselines. The paper is titled, Agentic Memory, Learning Unified Long-Term and Short-Term Memory Management for Large Language Model Agents. And as we'll see later, the way this system autonomously handles long-term context is really impressive. To visualize the core problem, Figure 1 compares the new framework against traditional architectures. On the left, the diagram shows a standard setup where short-term memory is static and long-term memory relies on simple triggers, meaning the two systems operate in isolation. The middle panel illustrates a common improvement where a dedicated manager handles long-term storage, but since short-term memory remains rigid, they still fail to coordinate effectively. In contrast, the right panel presents AgeMem. Here, the agent actively manages both memory types through unified tools, creating a synchronized system where short-term context and long-term storage inform each other. So Table 1 details the specific set of operations the agent uses to implement that unified strategy. The top rows list the long-term memory tools, where the agent can add, update, or delete entries in persistent storage to maintain an accurate knowledge base. In contrast, the bottom section defines the short-term memory tools. These allow the agent to retrieve saved data, summarize lengthy context, or filter out distractions, ensuring the active window remains efficient. Alright, having defined the tools, Figure 2 evaluates how well they actually preserve information. The charts display memory quality scores on the Hotpot QA benchmark, with the top panel using QN 2.57b and the bottom using QN 3.4b. In both scenarios, AgeMem, marked by the red stars, achieves the highest scores, reaching a peak of roughly 0.6. Crucially, the significant drop seen in the no RL points demonstrates that reinforcement learning is vital for teaching the agent specifically what to remember. Well, Table 3 explains that performance jump by tracking tool usage. The columns compare the baseline, labeled no RL, against the model trained with group relative policy optimization. In the long-term memory tool statistics section, the agent becomes more aggressive about storing information, with add memory calls rising substantially. It also begins actively maintaining that data, as update and delete operations appear almost exclusively after training. Similarly, the short-term memory tool statistics show the agent learning to manage its immediate context, evidenced by a sharp increase in filter commands to remove irrelevant text. So, Table 2 brings it all together with the final success rates. It compares agentic memory against state-of-the-art baselines across 5 different benchmarks, including complex environments like AlfWorld and SciWorld. Looking at the QN 2.57b section, the method takes the lead with an average score of nearly 42%, clearly beating strong competitors like Mem0. The gap widens even more with the QN 3.4b backbone, where it hits over 54% on average. Crucially, comparing the final row in each block to the no RL version just above it confirms that the reinforcement learning stage is the key driver of these gains. Okay, while the previous table showed the final results, Figure 4 breaks down the contribution of each component. Across 3 datasets, we see a clear stepwise improvement. First, the light blue bars show that adding long-term memory tools alone creates a massive jump from the gray baseline, doubling the score in SciWorld. The darker blue bars then confirm that adding reinforcement learning boosts performance further. Finally, the red bars demonstrate that the full system, which includes short-term memory tools, consistently achieves the highest success rates. Alright, having seen the components work, Figure 8 details the actual training algorithm. On the left, Part 1 outlines the rollout phase, where the agent builds experience by running through the 3 stages, constructing long-term memory, controlling short-term context, and finally reasoning. Then, on the right, Part 2 handles the optimization. Crucially, the loop in lines 28 to 30 broadcasts the single terminal reward back to every preceding time step. This mechanism solves the sparse reward problem, ensuring that even early memory actions receive credit for the final success. Wrapping up, 2 takeaways stand out. First, agentic memory successfully unifies long-term and short-term management by treating memory operations as learnable actions rather than fixed rules. Second, the progressive reinforcement learning strategy is critical, allowing agents to autonomously optimize how they store and filter information for complex reasoning. This points toward a future of far more adaptive, self-evolving models. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.